Okay, Al. So, our central goal today will be to talk about matrix equations and how to interpret them. You're probably familiar with some of this from maybe an algebra class, so I'm going to take a slightly different tact on this. So let's remember that we have a row picture and a column picture. So the first thing I'm going to talk about is the column picture because, again, this is probably the less familiar of the two. So in the case that I'm thinking in columns, right, I have an equation, let's say AX equals B, right? So A is some matrix, X is some vector, and the result of doing this multiplication will be some vector. I'm not going to throw in too much, oh, what the heck. Let's say A is a general m by n matrix. That makes X a vector in Rn as a vector space, and that makes B a vector in Rm. Oops, that's not where that m goes. Okay, so in this case, right, we have thought about A as columns. So we're saying, all right, this multiplication means that our vector B is, well, it's a scalar, it's the scalar coordinates out of X times the columns in A. So that's going to be, B is a sum of x1 times the first column plus x2 times the second column, and continuing until we get to, let's see, so how many are there? X was an n vector, right? So there should be n coordinates, and in fact in this m by n, we remember that's rows by columns, so there are in fact n column vectors to go here, right? For each of the input coordinates, there is a column vector. So this is my perspective, right? Is I'm looking at B as a linear combination of the columns. So when I consider trying to solve a matrix equation, right? When I have, say, a matrix like 0, 1, 1, 1, multiplied by a vector xy, and I'm wondering, when does this give me something, say, 1, 2? I might consider, okay, well, when does this happen? Well, let's see. So I have some options. The maybe first option that I have is, I could really think about this in terms of actually taking this first column vector, right? So if I'm thinking columns, right, I'm going to think, okay, so I've got x times 0, 1 plus y times 1, 1 is supposed to give me this vector 1, 2. Okay, when does that happen? Well, it seems that that happens when x is 1 and y is 1. And so my answer is that my x vector is 1, 1. That should hopefully follow. There are a lot of ones in this example, but I think you all got this, right? I'm asking which combination of the columns gives me this resulting vector. Now, this is contrasted against the row picture. So, in the row picture, I'm not asking a question about vectors, and this is kind of weird. So when I think about the row picture for A m by n times a vector x is B, what I'm really asking is, let's see. Let me think about writing this out. So if I wrote this out, I would get that my vector B, right, is the result of a bunch of dot products. It's the result of row 1 dotted with x, and row 2 dotted with x, and on down to row m dotted with x. Right, so this is what my B vector looks like. You guys all see this? So it's a whole bunch of dot products. If I don't know x, there's going to be a great number of variables in this thing. Does that sort of make sense? So let me consider what this looks like for my example over here. because this is maybe a little less obvious. I'm assuming that you've kind of seen this before, but maybe you haven't. So if I look at my example, oops, that's not an X. Okay, so in my example, I have my same matrix times my X vector is 1, 2. Now, if I look at the row picture for this, what I see is I have 0x plus y in my top equation. Ah, shit, I gave away the punchline. In my top coordinate in my vector. In the second coordinate, I have x plus y. And this is supposed to equal a vector 1, 2. Now, vectors are equal when all their components are equal. So this really boils down to two equations, which is really y equals 1 and x plus y is 2. You guys see this? So, what are these things? Well, categorically, these are lines. As long as I'm considering 2-space. Why am I considering 2-space? Well, because my xy vector was 2-dimensional, right? So, this row picture is a meeting of planes or lines. So this is a meeting of, I'm going to just call them flat things. But really, right, they're equations of the form ax1 plus bx2 plus cx3 up to some, in this case, n, right, equals some number d, right? You might recognize these as being lines or planes or hyperplanes or kind of similar objects, right? So there are two pictures to be had. The column picture, I wonder what linear combination of columns gives me this resulting vector, right? So that's fundamentally a thing about vectors. In the row picture, I wonder where is it that all of these planes meet? You guys see that? So when I find at the end, right, down here, I get, again, I get x as the vector 1, 1. And what that means here is that this is the intersection. This is a point of intersection. Right, and over here, this is really kind of a collection of scalars. Now, are those different? Settle on, well, no, but kind of actually, yes. So, are these really different? No. Essentially, considering things as the column picture gets you the same answer as considering things with the row picture. Now, but actually, yes, is that the interpretation is pretty different. And actually, I do a better job sometimes thinking in one way or the other. This is that kind of dichotomy of row picture, column picture all over again. You'll find that we switch back and forth views fairly often, and I think it's good to hold both in our head. So in the column picture, right, we find the scalars that linear combine to be B. Right, so we find the scalars for the linear combination of columns that give us this vector B. In the row picture, we find the intersection of all of these kind of surfaces. Really, they're all flat, right? So intersections of planes, essentially. We get the same numbers, but they kind of mean different things.